Okay. Okay, we're going to now go on to Ethernet frames, Ethernet switching and Ethernet frames. Anybody have any questions from what we talked about earlier to begin with? Or we're all good to go?
We're good to go. Or I don't have any questions.
Okay, great. Thank you. Okay. Right. So as I said earlier, that when we look at the data link layer, we're actually talking about layer 2. This is the second layer of 1, 2, 3, 4, 5, 6, 7 layers in the OSI model. The data link layer has two sublayers, LLC, and the MAC sublayer. And we also have IEEE standards that were written, and these standards at the 802.2 standards encompass only the LLC, but the 802.3 standards created by the IEEE actually encompass the lower half of the data link layer, the MAC layer, and the physical. So this standard does not line up exactly with the OSI model. And the model is just that. It's only a model. It does not constrain anybody actually, but conformity to the model tends to promote interoperability between systems. Okay. I mentioned the data link sublayers before, showing you that. Actually, all right. So yeah, we've seen that that little image before. Right. So now the MAC sublayer. This is basically where you're getting your addressing and error detection at layer 2. And we'll show you how that corresponds with the frame layout. But that's what's going on at the MAC sublayer. That's its responsibility. Okay. Now, they refer to 802.3 and 802.2 and how these are applicable to the OSI model and these layers. But out in the real world, we're not using generally 802.3 or 802.2. What we're using is Ethernet _2, which is a frame type that has been put into practice. So it's a standard de facto is what it's called, rather than a standard de jure. And the standard de jure has nothing to do with French day, it means law. So these are standards de jure. In other words, there's been some organization that actually created these and causes them to be implemented in certain instances. Whereas Ethernet _2, the frame type that we see predominantly in Ethernet networks, is a standard de facto. In fact, it's a standard, but it's not designated by any particular entity as having to be the standard. Okay. So let's look at what we have here. We have what's called a preamble and start of frame delimiter. These are the drum beats that are basically 1, 2, 3, 4, and go. We start with the destination MAC address, which is 6 bytes. Source MAC address, 6 bytes. And in the Ethernet _2 frame type, we have a type field. We don't have a length field. There are other Ethernet implementations that have a length field here, but we don't have to worry about that. Right now, what we should consider this field to be is only a type field. And the value of the type field will be more than 1500 because the length of an Ethernet frame should not exceed 1500. Okay. The minimum Ethernet frame type is 64 bytes. Maximum is 1518. Okay, so those are some numbers you would want to know. So we're going to have a destination and source address. And we know that the MAC address is 48 bits expressed in hex. And what we'd see, let me pull this out of the way there. So we're going to have 12 hex characters. And so basically your range is going to be from all zeros. That's right there. Our binary to all ones. Okay, that's just 8 bits, what they're talking about there. And we'll see what those different values mean. Now, when you express something in hex, you precede it with 0x. So 0x, let me get this out of the way again. 0x73 is telling you that the 73 is our hex characters. Okay. So now we see a MAC address. And let's just make sure we get oriented here. So we've got 48 bits with all this. 12 bits here, and I'm sorry, 24 bits here, and 24 bits here. So we have 16, I'm sorry, hex numbers here, hex numbers there. And basically, these all add up to 24 bits or 3 bytes. Each byte is 8 bits. These are actual indicated as ones, binary ones, not hex characters up here. So what we're showing you is you have, first of all, you have 24 bits or 3 bytes. And the first 24 bits is an organizational unit identifier. So here's what happens. You have someone that is going to manufacture Ethernet cards. That manufacturer will have to get a unique, organizationally unique identifier. In other words, only that particular manufacturer will have that particular OUI. Any card manufactured by that manufacturer has to have the first 24 bits identical to its OUI. So if we knew the different OUIs, we could look at a card and say, oh, this was manufactured by this company. Now, the manufacturer then, for every card it produces, assigns a different address down here. So these 24 bits are going to be unique for all the cards within that manufacturer. So a manufacturer should never put out 2 cards that have the same OUI and the same vendor assigned ID. Okay. So what's going to happen is that when a message is being sent, so we have something being sent along this wire here, a receiver is going to first look at the destination address and decide if the destination address is its own address. And if it is its own address, it's going to take that particular frame in and process it. If it's not, if that frame is not intended for that machine, after it's processed the destination address, it simply stops the processing and throws it away. Okay, so let's look at the addressing types. So in this world, there are basically, and this is not completely, there's one more in addition to these 3, but there are 3 basic types of addresses that we encounter. A unicast address refers to a single entity, and all of us as people have a unicast address. That's our name, okay? There is also a broadcast address. A broadcast address refers to everybody in the world, and we are all members of the group, everybody in the world. So we would respond to a unicast address and to a broadcast address if someone were to communicate with us. The third type of address that we encounter is a group address or a multicast address. And a multicast address refers to a particular group, and all of us would respond to various multicast addresses depending upon which group we would consider ourselves a part of. So if someone were to say, I'm going to send a package to all the people living in Southern California, and I'm down in Palm Desert, I would say, oh, I'm a member of that group. I'm going to get a package. We would say, I'm going to send something out to all the students at Cabrillo. That's a multicast group. I'm going to send something out to all the students in my class. That would be a smaller multicast group. So there are multiple groups out there and addresses that can be associated with those groups. In the world of Ethernet, if you're sending to everybody, that's a broadcast, and the address is all ones in binary and all Fs in hexadecimal. So if you see an address all Fs, that is a broadcast address. A broadcast address should never be a source address. You never send something and say, hey, I'm representing the whole world, okay? So you would always have, if you're sending a broadcast out, the source address would be your unicast address. The broadcast address would be the destination address in the frame. Now they say something here that's true. A broadcast address is flooded out all, I want to put this right here, flooded out all Ethernet switch ports except the incoming port. And it's more specific in that. As we talk about switches more and more, we'll understand exactly how that works. But basically, when you send a broadcast address, a broadcast frame to a switch, it's going to normally send it out all of the other ports to all the other devices connected to that switch. And when you have to put a caveat or an exception in the same VLAN, we haven't talked about VLANs yet, though, so that wouldn't necessarily make sense. Here we're looking at multicast addresses. When you see a multicast address, the first 24 bits are going to be that 01005E. The next 24 bits are going to be constructed in different ways. Don't worry about that now. But basically, if the first 24 bits of the destination address are that, then that means that the address is a multicast address. And the last 24 bits will be used to designate some group. Now, the way switches work is switches forward frames based upon the destination MAC address, okay? So what it has to do is keep a table of MAC addresses and the ports out which it learned that particular MAC address. So essentially, we have what's called a MAC address table, sometimes also called a CAM table. But basically, you have the one or more MAC addresses learned out a given port on a switch. So the switch keeps that information in a table, and when a frame comes in, it looks at the destination MAC address, and it looks that up in its table. And if it knows about that MAC address, in other words, it has an association in its table between that MAC address and a port, it will send that frame only out that port. However, if it doesn't know about the MAC address, it's called an unknown address. And therefore, at that point, it can't know which port it should go out, and it sends it out all other ports, except for the one it came in on. So what we see here is that a broadcast address and an unknown address are treated the same, okay? When a switch is turned on, there is no MAC address table. At least it's not populated at that point. Therefore, as a switch first goes into operation, it begins flooding frames based upon destination addresses. But as it learns where the different MAC addresses live, it then only forwards frames out those ports. It learns from the source address. So if you have a station, we'll see this in here. We have a, here, let me just jump down here, down a few slides. So we see here, port 1 on the switch has a station out here with a MAC address that is 000A. When this particular station sends a frame in, the source MAC address will be 000A. Since it came in on port 1, it now can put that into its MAC address table. If this machine over here, 000D, responds back to 000A, or the machine A, the switch will not forward that return frame out these ports because it knows from its MAC address table that 000A lives right there. But if it did not know where it was, it would send it out these others as well. Now I'm going to back up here a little bit to where I was. Yeah, there we were. Okay, so right there. So this is what I was referring to. The way it learns, a switch learns from the source MAC address. That's how it builds its MAC address table. An entry is kept in the table for 5 minutes in many switches by default. You can change that, but generally if something's not used within 5 minutes, you just as soon have it aged out anyway. It forwards based upon the destination MAC address. This is, in a nutshell, how a switch works. You might say that it's a plug-and-play device, maybe the most plug-and-play device, because when you simply power up a switch with devices plugged in, the switch begins working right away. It begins learning where MAC addresses live, but until it knows, it will simply flood things out other ports. So frames will still get there, but as it learns and then can filter on the forwarding, it reduces the amount of unwanted packets that destination machines would get. Of course, if it's a broadcast or a multicast, it will always flood except the incoming port. And the reason is it learns from the source address, and the source address will never be a multicast or a broadcast. Okay. Any questions so far about switches? We're good? Okay. All right. Now, we're going to get into now is some forwarding methods. These things that we're covering right here are things you need to know for the test. There are times when you might also want to know these if you're making a buying decision. For the most part, though, out in the world where you're working with higher end switches, they're all going to use store and forward switching, and there really isn't going to be any reason for you to configure it otherwise. But here's what's going on. And we actually can refer to some things in the trailer of the frame to explain this. So with store and forward switching, what happens is a frame comes into a port and is put into a buffer. Once the entire frame is received, in the world of Ethernet, the receiver calculates the CR, actually calculates the FCS, frame check sequence, using a CRC calculation. So CRC stands for cyclic redundancy check. So basically it performs a mathematical operation on a number that is kept in the trailer of the frame. And the way it does this is basically it's performing a calculation on the rest of the frame and sees if the calculation results match what is in the field where the frame check sequence is held. And the frame check sequence is arrived at by the cyclic redundancy check. So again, if I could switch over to a whiteboard very quickly and get back, I would do so. But basically, if you send a frame, you've got all these ones and zeros. When you're the sender, you perform a CRC or a computation on all the ones and zeros using this algorithm. When you have the results of the algorithm, you put the results of the algorithm into the trailer, and the results of that algorithm are called the frame check sequence. So the frame check sequence is the value, the CRC is the calculation. When the receiver receives the frame, they perform the same computation on the same portion of the frame that you did, and then they check and see if they came up with the same value that you put into the frame check sequence. And if the values match, then the receiver assumes that the frame arrived intact. If the values don't match, the receiver assumes that the frame was damaged somehow in transmission, and it simply throws the frame away. It does not send back a message to the sender saying, I got a frame that was bad. It simply discards the frame. Now, this happens at the switch when it's using store and forward switching. The switch gets the frame on a port, does the calculation, and checks the frame check sequence that is contained in the frame trailer. If they match, that's great. It then is going to move that frame on to the next port or ports to send it along. If, on the other hand, they don't match, what it will do is discard the frame. So with store and forward switching, you will never send on, a switch will never send on a bad frame. Now, with cut-through switching, there's two different methods we're going to look at. You don't have to wait until you get the entire frame in to forward it. So let's look at what that means. We have two methods of cut-through switching: fast-forward switching and fragment-free switching. So let's look at fast-forward switching. We know that the destination MAC address is in the first 48 bits, or that would be 6 bytes, right? So the switch can make a determination as to where a frame is to go next before it's received the entire frame. But we know that what can happen is that there could be a collision on that frame that could happen before the first 64 bits arrive. So what can happen with fast-forward switching is the switch might actually forward a frame that has been damaged, and that would be a fragment. It would be forwarding a fragment because it's not getting a full 64 bits. With fragment-free switching, the switch does at least get the first 64 bits. It still is going to do a fast forward based upon the destination MAC address, but it's not going to actually forward until it's made sure that it's got 64 bits. At that point, the switch knows that in fact, there wasn't a collision if everything is running at specifications, but it doesn't know whether or not there was an error check or an error on some other part of the frame. So it could be forwarding a frame that has an error in it, but it will not be forwarding a frame that has been the result of a collision. Okay. And you need to know those for the test. Again, you can sometimes configure those on switches. For the most part, with today's performance capabilities, what you're really going to do is just stick with the store and forward. Two different ways we can buffer or put into a type of memory. Buffer is a form of memory. Buffer incoming frames. We can actually buffer it at the port, which will not be a large buffer, or we can buffer it into the basic memory on the switch, would be shared memory. Now, what you have with twisted pair is you have multiple wires in your actual cable. There's 8 wires, but what you have is a send wire and a receive wire that are separate. And the send wire on one end goes to the receive wire at the other end, and vice versa. So what that means is, if I send something across an Ethernet cable and it arrives at the other end's receive wire, there can be no physical collision across that particular portion of the trip because it's not in contact with any other wire. If we are in a half duplex state, we are listening even on that wire that's coming in that could not have a collision on it. We're listening for a collision. What would be more efficient is if we disabled collision detection and then went into a full duplex mode, because in a full duplex mode, we can send on our send wire and receive on our receive wire and know that there is never going to be a collision on anything coming on those two if the network is properly set up. So what we want to do is operate in full duplex across these switch connections, as long as we don't have a hub involved in the middle. A hub would force us into half duplex mode. But if we have a switch port directly connected to a workstation, then the send on one end is going to the receive on the other, and it's safe to go into full duplex mode. In fact, it's most efficient to go into full duplex mode. And this can be negotiated between the two ends. Speeds can also be negotiated. You want to make sure that each side is operating at the same speed. So you might have one operating at 10 megabits per second, the other operating at 100, and that won't work. And then we have currently auto MDIX. And what that means is that basically the switch is going to be able to detect exactly the speed and the right duplex settings for each port and use those settings accordingly. All right. And that takes us, we're going to stop with that. Okay. Let me see here. All right, let's switch over to Packet Tracer and look at switching. So I'm going to pull up Packet. I'm actually have to stop the share. pull up, get packet tracer going. Okay. So now hopefully everybody can see packet tracer. You see I have a switch there. And let's just talk about what's going on in this little environment here. So from here to here, an Ethernet frame can be sent, or in either direction, let's say. And when it gets to the switch, we just want the switch to forward it out the proper exit point, and the port that's associated with that MAC address. If we were to look at this switch, and we will just a second, we'd see that the switch should have learned about the MAC address up here is living out this port, and the MAC address down here is living out that port. I'm going to switch to the switch now. I have to stop my share and do another share there. Okay, and I'm going to bring this up here, and we'll see whether or not, okay, EN. And let's do a show MAC address table and see, okay, so at this point, it hasn't learned anything. What I'm going to do is switch over. I'm not going to switch the screen that you see for now. I'm going to do this back in Packet Tracer, and then I'll come back to this. I'm going to cause a ping to be sent and see if I can make this thing work. Okay. Let me okay, the addressing there is fine. I'm doing a little troubleshooting here to see if I can see why my ping isn't going through. Okay. So I still don't have a successful ping for some reason. Okay, so I'm going to now come back to the switch. Yeah, shared. Reissue this command. I have issued some pings, but I'm not learning about, there's something going on with the configuration here. Let's do a show VLAN. I just want to see if there's any configuration. VLAN 1. Let's do I'm doing a little troubleshooting here to see why we. Oh, that's interesting. So I'm thinking that I've got some connection in here that isn't quite set up right, because I'm not seeing any neighbors, and I should see a neighbor here. And I'm going to pop back out again, just do a real quick analysis. Oh, Okay. Well, I'm not sure what, it's probably a cabling issue. Because I've got a, Armando, you said you had yours working?
Yeah, I do.
You can ping from the router to the PC, correct?
Yeah, I can.
Okay. So let me try something here. Because the switch is not showing any neighbors, which tell, oh, there it is. Okay, so the connection between router one and switch one is working. Now we see that. Let me just see if I can generate a ping. And nope, the ping is still not working. Okay. Okay. So let's go. I'm going to go to my IP config, make sure I've got that right. Oh, suddenly I don't have an IP address here. See if this fixes it. Oh, I see. Okay. It was a little fat finger. I actually got the addressing wrong. Oh, okay. Somehow I got the address into the Bluetooth. I must have left it myself in there. Boy, that's interesting. Okay, fast Ethernet 1. For address. Huh. I don't know how I messed that up, but I think when I went in and demonstrated the other one, let's see. Okay, so it doesn't like that addressing, and I'm not seeing how. Oh, I know what I'll do. I'm going to um, okay, I'm going to delete this device. Okay, and put one back in there. Cable it real quick, and I'll just get this thing going in just a second. There we go. And I should have this thing working in no time. Okay. Yep, there we go. Okay. So now that works. Bring up the switch, and here we go. All right, so now I have the switch is properly connected to each end, and the pings are passing through. I do a show MAC address table. Well, there we go. How come I should be seeing that information in there, and I don't. Let's send another ping through real quick. Okay. Switch. There we go. Okay. So this is what has happened at the switch. The switch has learned about these two MAC addresses. One is out FA01, the other's out FA02, and my guess would be that FA01 points up to the router and FA02 points down to the PC. And if I do a show CDP neighbor, which we don't have to worry about understanding fully yet, yes, FA01 is the one that points up to the router. That's the router. My interface, FA01, is connected to the router, and the router is looking at me through its port fast Ethernet 00, and that means that the router's MAC address on that interface is that right there, that, okay? So that's how simple switches can be. I really didn't have to do anything to it. Just got the cabling and addressing correct, and away it went, and it's learning about where the different devices are. Okay. Right. Any questions on that? Okay. All right. So what I'm going to do now, let's make sure I've got the right one up. Yes. Zoom here. Okay. So now we're going to look at the network layer. And, normally, of course, if we were in a, full semester class, this would be about halfway through the semester, not, the third meeting in. All right. So the network layer is layer 3. And at the network layer, we're looking at addressing again, but now we're looking at logical addresses. And logical addresses have a location parameter to them. So, they have something that tells you where they are. And then IP, that's the network address. So IP version 4 and IP version 6 are both network layer addresses and addressing schemes. When something is handed from above down to the network layer, it is encapsulated and then sent out. Along the way, it may be routed if routing is called for. At the other end, you get de-encapsulation and handed up to the proper protocol running above. Okay. So if we have something coming down from the transport layer, which would be layer 4, the transport layer puts on its own header, adds it to the data that it received from above, and that comes down is now the data for the network layer. And if we're looking with IP hands or adds its own header here, and then that gets handed down to the MAC layer or layer 2. Okay. So some things that we can say about IP, and we'll look at what these actually mean. Connectionless, best effort, media independent. Let's look at what those mean. So connectionless. An example that they have right down here is a good one. When you send a letter, you address it and you put it in the mailbox and you hope it gets there. you don't first call up the other person and say, I'm going to send you a letter. You usually don't. And say, I'm going to send you a letter. When you get it, let me know, and then send off the letter. So when you simply address and send something, that's called a connectionless communication. And what it means is you haven't talked to the other side first before sending. There generally is also not control information. In other words, there's not going to be acknowledgments coming back and other aspects to controlling the flow of this information. Okay. When a communication needs to be connection oriented, IP does not get involved with that connection. That's handled by TCP at the layer above. IP is always only concerned with getting the addressing right and sending it off. And if it gets there or not, generally it doesn't know. If it gets there and it's damaged, IP is not looking for a notification that there was a damaged packet that was sent. If it gets there and it's intact, IP is not looking for an acknowledgement that it got there. So it's a connection less. And because of this, because there is no acknowledgement, there's no resending, then you also can refer to this as best effort. And often best effort and connectionless go together. So I'm going to send this packet from there to there. Hopefully the router is going to get it there, and we're each going to do our best to get it across. But if it gets lost along the way, no one's sending a message back with IP itself. The IP protocol does not send a message back that, hey, it got damaged, resend it. Now, upper layers like TCP can send messages back and said, I never got that, but IP itself does not. Because we don't have any of this mechanism for assuring that it got there, IP is also referred to as unreliable. Now, that doesn't mean that IP is unreliable in the world in which we live. Obviously, it's extremely reliable, but we cannot say that it's really guaranteed reliability. It's just hopefully reliable all the time because things work. But if something doesn't work, IP cannot fix it. Protocols up above will fix it. IP is also media independent. It doesn't matter whether you're going over Ethernet, going over a WAN connection, a fiber connection, wireless. It doesn't matter to IP. IP is basically part of the data in the frame. As far as the layer 2 data link layer is concerned, IP header and the data that it's carrying is all just data. So you might say it's like an Amazon package. What's in the package, it doesn't matter how the package is sent, whether they send it by airplane, by train, by truck, car, motor scooter, does not matter how the package gets there as far as what's contained inside. IP has an MTU that it determines based upon talking to the data link layer. And what can happen with IP version 4 is that, for example, let's say I send something across here that's 1,500 bytes. And then I'm going to send it there next, but let's say this only allows for 1,000 bytes. Now that wouldn't be typical, but let's say that was the case. I've got 1,500 bytes got here, but only 1,000 bytes is allowed across there. What IP can do is break that into fragments. Now, what you'll notice is that when the data up above is broken into parts, by layer 4, we call it segments. But when layer 3 does exactly the same thing, break it into smaller parts, we call it fragments. So if a large packet comes in here and multiple smaller packets have to leave here, each of those is considered a fragment, an IP fragment. That doesn't mean that there's something wrong with that. It's not, all the fragments can work just fine, but it does mean that the original data has now been broken up into smaller packages, okay? And that means it had to cross a smaller MTU, maximum transmission unit, right up here, maximum transmission unit. We don't see this a lot today. The reason is Ethernet's at 1500, and pretty much everything in between will be 1500. In the olden days, when there was a lot of token ring out there, token ring had an MTU of over 4,000, 4202. And so if you sent something off in token ring at 4202, and it encountered a segment of Ethernet, it couldn't go across that segment without being fragmented. And a router could do that, fragment that into smaller fragments, and then the fragments would go across. And at that point, they would all be received at the destination and be reassembled. And so there had to be sequence numbers that were properly put into the IP4 header so that it could be reassembled properly. So let's look at more detail here at the IP4 packet. Okay. So something along the way that has to forward based upon a layer 3 address is called a layer 3 device. That's really all they're saying there. Now, here's way too much information all of a sudden, okay? So let's not worry about all of this because it's a lot to take in. I want to just focus on a few of these here. So first of all, we have a version field right here, okay? If it's IP version 4, it's going to say IP version 4. And that, of course, is important to the receiver to know which version of IP it should be using to interpret the rest of this. Let's skip all of this right there. Go down to a time to live. Okay, so the TTL, this is a very important field in an IP header. And what happens is each operating system, when it sends an IP packet out, it has a default time to live value that it uses. And it's not really important which value it uses. Some of them are like 128, and the other one might be 64. It doesn't really matter because usually it will never really come into play. But here's what happens along the way. When a router gets a packet and forwards it, it decrements the time to live by 1. It doesn't matter how long it stayed in the router or how long it didn't stay in the router. When it goes over a router, the time to live is decremented by 1. Now, if a router gets a packet and the time to live left in it is 1, it would then be decrementing that to 0. And when a router decrements a time to live value to 0, it throws the packet away. So if I were to send off a packet with a time to live of, let's say, 64, once it crossed 63 routers, it wouldn't be able to go any further because it would have been decremented along the way. I think that numbering works out, but you get the idea. Each router along the way would decrement the time to live value, and when it got to 0, the router would not forward it. This is actually a field that is used by certain utilities. For example, a trace route uses the time to live field, okay? You should never run into a problem because normally they're set so high that that would be very unlikely you'd very, very seldom ever go through something like 60 routers. I mean, to go through, 10 to 12 might happen, but something like, 60 routers would just be unheard of. Something would generally be wrong. You might say, well, okay, so why do we care about that? Well, this is a good thing in the world. Let's say if you got a packet that got into a loop, it just kept circling around in a loop. Every time a router processed that, it would decrement the time to live by 1. And eventually in that loop, it would be decremented to 0 and thrown away. So it wouldn't stay in the loop forever. It would only stay in there long enough to decrement the time to live to 0. Okay. Now, the next thing here is the protocol field. The protocol field is where this goes to next up above, not down below, but up above. So if data is handed to it by TCP up above, and the IP header is going to be put on the data that's handed down, IP will indicate in the protocol field that this is from TCP. When it is then encapsulated at the other end, when the receiver reads this protocol field as being TCP, it will hand the data that came in up to TCP. So the protocol field is very important. We then have, as we would expect, a destination and source address that happen to be in the reverse order, but that's not a problem. The devices know how to read it. And so the destination IP address is used to make forwarding decisions. And at the ultimate destination, it's used by the receiver to know that that packet was for it. Okay. We can talk about these 3 fields up here at another time, but I don't want to overly complicate things right now. Okay, so just a few things that I went through here. Version, time to live, protocol, source, and destination IP address. If you get into differentiated services, that's a whole nother mess in there. We don't need to talk about that. Also, what I'd like to not do is go through IP version 6. I like to stick with IP version 4 for a while and get comfortable with it, and then we can bring in IP version 6. The headers are different. The reasons for that are, make sense, but anyhow, what I'm gonna do is skip on to how a host routes. So now we're talking about how a router works. And we will touch on briefly on IP version 6 here, but for the most part, we're looking at how a router is going to route and how a host would be the source would send things off. Okay, so our host creates a packet. And when the host creates a packet, there's actually 2 places it sends it to. Normally, you're not sending to yourself, but this would be a 3rd place. If you could send it to yourself. If you're just testing your own system, you send it to yourself. Otherwise, packets that you're generating go to local hosts that are on the same LAN or remote hosts, not on the same LAN, a remote LAN. So you might say, when we send packets, they're either local or remote. That's the 2 destinations that we normally use. When we are the source device, we have to determine, are we sending it locally or are we sending it to a remote network? If we're going to send it locally, I like this, dumped out the host interface. Okay, that's pretty good. Local traffic is sent directly to the destination. Remote traffic is sent to the default gateway or the local router. So basically, you're going to send something directly to the destination or to your default gateway. You will have a default gateway normally being a router or layer 3 switch, which is acting like a router, even though they're calling it a layer 3 switch. So your default gateway is an address that exists on your network. And you have to be able to reach that in order to get things off your network. If you do not have a default gateway, you cannot communicate off your own network. It's that simple. And what you do is you compare the destination IP address to your own IP address. And then you apply the mask, your own mask, to each. So, and we don't have some numbers here, but in the example, the scenario that I sent out, we have the PC is on network 172.16.1.0. And the other PC is on network 172.17.1.0. If you apply the mask of 255.255.255.0 to both of those addresses, they are not the same. The result is not the same. That means that they're on different networks, and then the PC, to get to the other network, sends to its default gateway. Okay, so let's just look at routing here briefly, and then we can wrap up. So what a router is going to do is forward based upon the destination IP address. And where it's going to find that destination IP address is in its routing table. It learns about a route one way or another. It has to learn about the route first. It then has to learn what interface it goes out, and possibly what is the next hop along the way, the next router along the way. So we have routes here, and then we have where it goes next in our routing table. There are different ways that we learn about routes and different types of routes. Okay. So when I activate an interface on a router, I give it an IP address and I do a no shut. Because I put a mask with that IP address, the router then learns that out this interface, in this case, the 192.168.10 network is out here, and it can put that in its routing table. When you activate this interface and give it an address, it learns that the 209.165.200, 224, that's probably a 31, yeah, 30, I mean, 30, it learns that that network is out there. And they can go into its routing table as directly connected networks. This router here might send information to this router about this network. And that would come in this interface from that router. This router then can put information about this network into its routing table, and that would be a remote route. If it learned it from another router, it's learned dynamically. If you configured it as an administrator, then you did that manually, and that's called a static route. Okay. Now, there's another type of route, which is a default route, and basically says, if I can't find it in my routing table, I send it wherever. For example, in this case, this router knows about these two networks because they're directly connected. It learns about this one through either a static route or this router telling it dynamically, but it doesn't know about all the rest of the networks in the world. So what you could do is have a default route here that says, if you don't know where to send it, in other words, it's not in your routing table, send it there. And then this router would have a default route that says, if you don't know where to send it out that way. So that's default routing is a very important part of routing. Not hard to configure, but extremely, extremely important to get right. Now, static routing is where you, as the administrator, configure that with a command. And you see here the command in the global config mode is IP route, and then you put in the destination network, the mask that goes with that destination network, and then the next hop router. So in this case here, on this router here, to get to this network, 10.110/24, which is the same as 255.255.255.0, you send the packet next to 209.165.200.226, which is that address there. So that's the next hop. That's the destination network. Static routing is useful in many circumstances, but it is not something that works. It's not very scalable. So often you will have some static routes in your network, but often in conjunction with that, you'll also have dynamically learned routes. To learn routes automatically, we are going to learn them generally from another router. And what the other router is going to do through what's called a routing protocol, the routing protocol will be used to communicate between these two routers. And the routers will tell each other about networks that they know about. And then each router can keep the other router updated as network availability changes. Okay. When we do a show IP route, we get all sorts of different information here. And we see here L for a directly connected interface, C for a directly connected network. So this is something that wasn't always the case. These two are pointing to basically the same thing. This is the interface. This is the network connected to that interface. Static route that you manually configured, and then if it's dynamically learned through routing protocol, and two that we cover in this class are OSPF and EIGRP. So we'll eventually learn about those routing protocols. There are other protocols that could be running out there that would be used to pass information about networks, but these would be the primary ones used in this class. Okay. All right, that takes us through that module, and that I think is module 8. Yes. Let me just see whether I want to go to module 9. Okay, we can talk with we can. Are you folks seeing module 9?
Yeah.
Okay, so it flipped over the share real quick. All right, good. All right, we'll do a little bit on this and then we'll wrap up. Okay. So let's look at MAC and IP, the relationship and what's going on here. And now we've sort of gone away a little bit for routing, but this will tie back into routing. So what we have here is a PC here and a PC there. The fact that there's a switch in between is irrelevant for what we're looking at here with the relationship between MAC and IP insofar as the actual forwarding. But so we've got a MAC address here and a MAC address there. But when we send from here, as you may have encountered out there, is you send to destination based upon their IP address. In other words, that's what you look up. You do that through DNS. When you go to a web destination and you get the URL, that gets translated into an IP address. Well, going from here to here, we're going to use a frame, and in the front of the frame is the MAC address. So how do we learn what MAC address goes with this IP address? We're sending from here to here. We know our destination IP address is that, but how do we learn about the MAC address associated with that IP address? Well, it's done by way of something called ARP. Okay. Now, when we're going to send to a remote network, this is where the routing comes in. Now we're here, we want to send to, let's say, something out here. We know that it's remote because when we put our IP address and its mask against that IP address and our mask, we know that they don't match, and therefore these are on two different networks. So we have to first send it to the router. Well, now what we have to do is we're back basically to the scenario of the previous slide. We're sending to the router. We know the router's IP address because that is our default gateway, but that's not going to be anywhere in the IP field. What we need is to fill in the layer 2 header, the MAC address. And so what we need to do is say, okay, given that we want to send to the IP address on that interface, what's the MAC address that goes with it? And what we use is ARP, Address Resolution Protocol, okay? And essentially what we're going to do is resolve an IP4 address to a MAC address. We will maintain that in a table, but ARP is primarily about the resolution, and we have an ARP table for a while as addresses are resolved. So this is something that you would want to understand in the world of networking for all sorts of purposes, troubleshooting, as well as routing, switching, etc. Okay, so if the destination IP4 address is on the same network, then we're sending to a local address, and we search the ARP table for the destination IP4 address. If it's on a remote network, we're looking for the MAC address of our default gateway. Okay. If we don't find anything in our ARP table, then we send an ARP request. And it's really that simple. You can remove entries from the ARP table. Very seldom will you do that. Maybe if you're having some troubleshooting issues and you want to mess around with it manually. For the most part, the ARP table is automatic. It will populate itself automatically, and you can view it, but generally you're not going to tinker with it. If you're on a router, you want to see the ARP table, show IP ARP. We see here that destination IP address has a hardware address of that, and it's found out that interface. On a Windows machine, your PC, the command is ARP-A. Yes, you need to know that for the exam. ARP-A, and you're seeing that out this interface. You've learned these addresses, and each of these addresses has these MAC addresses or physical addresses. And you learned that dynamically. That was not entered manually by the administrator. You have a couple issues that come up around ARP. It's not something that's real popular in the sense you might say with network administrators. One is that if you're going to find out someone's MAC address and you have their IP address, you have to send a broadcast. And broadcasts are not welcome on networks, so that's a bad thing. And the other thing is that we call it a threat actor, which could be anywhere from somebody trying to attack your network or intercept packets, whatever. They use the term threat actor. If someone sends out an ARP, let's say, to get the default gateway MAC address, if we reply back with our own MAC address, then they'll send packets to us. We can capture those packets and then move them on, and they won't be aware that we're capturing their packets. So we have different things, as they say, mitigation techniques to protect your workstations. And we get into that a little bit in this course in the security section, okay? And that's that. Let me see, what have I got? IP version 6, we don't want to deal with that right now. And module, okay. So that takes us through this evening's modules. And what I would recommend you do is take the scenario which I sent out, very simple, make it work and look at those different commands. Show IP ARP on the router, do an ARP-A, do your pings, look at the MAC address table on the switch, and practice putting in your passwords, etc. All the things that we did tonight. It won't take you real long, but just go through and configure those three devices on one side is all you have to do, really. Configure those three devices, and that'll give you a good practice to cement in what we've done. You can do it where it's not necessarily tonight, but over the next couple days. I hopefully will be back in Southern California next Thursday. In any case, I will see you online from wherever I happen to be, hopefully. And I will, I forgot to post the recording. I'll try and remember to post that right after tonight's class. Any questions about anything that we've covered or haven't covered?
Yeah, I have a question about the test. So,
About
is it like,
CCNA?
yeah, is it like, um, are we gonna have to like set up like routers on the packet tracer or
What they
just,
have, and I would have to go back and see whether they still, I think they still have interactive questions.
yeah, that's what I meant. Like,
Yes, an interactive question, which you are given a simulator of some sort, and it's not a full packet tracer. It's a very limited simulator
oh,
for that particular question. And then you would go to the command line and possibly issue commands. Now, to the extent that they still have those, they used to be called lab questions or interactive questions. It used to be there were two major lab questions. I think they have taken those off the exam. And I think one reason why they took them off the exam is because people learned about the lab questions in advance. There were actually scenarios out there. And when I, many, many years ago, taught a CCNA exam prep course, I actually had access to those scenarios. And I was able to teach people how to answer those questions. I wasn't trying to, cheat, teach them how to understand why they were doing things the way they would be doing it. And but I think that the lab questions became so devalued because of the availability of the scenarios. So there will be
okay,
some interactive questions, I believe,
okay,
that you'll find.
for sure. Thanks.
Yep. All right. All right. Have yourself a good next couple days, and hopefully things won't get like they were yesterday.
Hey, you too. Well, see you on Tuesday.
All right. Take care.
Bye.
Bye-bye.